Maybe you don't need to totally understand the operation of your home forced air heating system as we explained in part 1 of this video series, but it helps to have something to compare to when trying to understand the operation and benefits of a PID loop controller as used in an industrial process controlled application. Another application that may be thought of as making use of a PID loop control would be the cruise control in your automobile. Turn the cruise control on, press set when you are at the speed you want to maintain. A sensor measures the vehicle's current speed, while a small computer running a PID program compares the set speed to the current speed and adjusts the vehicle's throttle valve through a vacuum actuator, with the result being your speed is maintained. Up and down hills pose no problem with the vehicle automatically accelerating and deaccelerating. Press the Accel or Coast button to adjust your speed in 1 mile per hour increments. Press off or use the brake and you are back in control. It is only fair that we give you a short explanation of what's behind the working of a PID. To better understand how a process is controlled with the use of a PID loop controller, such as the feature available in the Productivity 3000, take a look at the key elements as shown here in a typical PID loop diagram. We enter the end result we are looking for as a set point value. We have the ability to measure where the current or real-time process stands. This measurement becomes our feedback, which we reference as our process variable. The set point value is compared with the process variable, and the differences between the two values become our error term. The error term value is used with the proportional gain value to produce how much correction we need from the PID output to force the process variable closer to our set point. The question that comes up now is how much proportional gain do we need? Take a look at just the proportional term in our PID formula. If we have too little gain, it will take a long time for the process variable to get to our desired target when a change is made to the set point. If we are too aggressive with the gain, our process variable will overshoot our set point and possibly start oscillating back and forth around the set point. Ideally, we want the gain set to a value that will produce the shortest response time getting to the set point without a large overshoot or oscillating as seen in diagram 3. Here we see the typical formula that is used to determine the process output based on the calculated proportional gain, the integral time, and the derivative rate. It helps to keep in mind that the proportional gain acts on the present error. The output correction is further modified by the integral rate value, which is calculated from the accumulation of past errors. The derivative rate, when used, is included in the final output correction based on a prediction of future errors, with future errors being determined by the current rate of change. Our example PID loop control application that follows will also include a method to set the desired result, or the set point, monitor the effective result, or the process variable, but instead of an on-off condition of the output as in the home heating control system, our example PID loop controller will be able to vary the process output anywhere from off to fully on as required during the operation. Any error between our set point and the current process variable will be handled by our PID loop calculations. Our set point will be the desired volume in gallons of liquid we require in the process tank, and our process variable will indicate current volume based on the liquid level measured by an ultrasonic sensor and converted to gallons. Join me for the third video in this series in which I cover the PID loop application example and also explain the hardware that was used to create our working demo.